Hey, hello. So it's time to our last talk of this CART 2025. So I like to introduce you the Professor Canek Peláez Valdez. Canek is working in the mathematics department of the science faculty of UNAM in Mexico. And I meet Canek maybe when he looked like the picture of the presentation. Yes, when you were a master degree student, I think that was the first time that we meet. And I think we were in some conference together, but after this, Canek finished the PhD, and after some type of competition in Mexico, he obtained the full-time professor teacher in our faculty. So it's really an honor for me to introduce now to Canek as my colleague of the department. So thank you very much, Canek.
Thanks to you, Rita. I will share my screen.
Yes.
So I think everybody is seeing it, right?
Yes, it's okay.
Okay. Well, first of all, thank you, Rita, for inviting me. And I always see the notification of this conference, but I haven't been able to attend, and I was really honored that you invited me. Also, you invited me like with 4 weeks of notice, so I did what I usually do in this kind of situation, and I say, okay, I will not present anything that I'm really doing. I will take the work from my students and take credit for them for them. But basically, I'm going to talk about three thesis projects of three students of mine that already graduated. As Rita was telling, I finished my PhD in 2014, and I was working in the in the electoral authority here in Mexico, working in this kind of problems. Yeah, and it was eye-opening for me because the computer science programs in Faculty of Science in UNAM is pretty successful in forming professional programmers. Basically, the notion of a graduate from the program that is unemployed is non-existent. All of graduates find work, most of them usually as programmers, but there is also people that continue to study and they make their PhD, etc. But they usually work in the industry in the kind of problems that the industry handles. And as I was saying, I was working just before getting my PhD. I was working with the electoral authority here in Mexico, INE. At that point, yeah, in 2014, it was already INE. Before that, it was called IFE. And I was working with David Romero, a colleague of ours that unfortunately passed away during the pandemic. But the kind of problems that the electoral authority has to handle, in this case, in that case, it was the districting problem, which is a really, really interesting problem. Opened my eyes to the kind of stuff I would like our students, the students graduating from the computer science program in Faculty of Science, to be able to solve by themselves even before graduating. So when I started to be a full-time professor, I began a seminar where students choose NP-hard problems, which we'll discuss in a moment, and they make practical implementations of systems to solve these problems. Many times in the academic world, the people that program these systems, the systems to solve NP-hard problems, are not trained to be professional programmers, which is fine. They get the job done. However, they don't know, because they don't need to know, they are not trained in like a professional programmer. And I wanted to bring the students of computer science to these kind of problems. So I started this seminar. And from that seminar, several students of mine choose to take up a problem and use it for the thesis, the final project to graduate from the program. So since Rita told me about this talk something like 4 weeks ago, I said to myself, I will present the work of my students, and then I don't have to work that much myself, and it's easier for me. So the students which work I will present are Alejandra Coloapa, Carla Garcia, and Marisola Amezcua, and I want to be very clear that this what I will present is it was work that they did. I was their thesis advisor, so my work basically consisted of prodding them with a stick every I don't know, couple of months, asking them if they had finished it or not, and everything else, everything important in those works, they didn't by themselves. I'm just presenting what they did. Okay, so let me start. In all the instructions for these talks, there was some kind of emphasis in that they're part of the public, of the audience for these talks, not necessarily are familiar with the topics we discuss. So I will give a quick introduction to NP-hard problems, and then I will talk about the work of my former students. So okay, we will call NP problems those problems that we can verify if a candidate solution it's indeed a solution in a quickly way. I will not go deep in what I mean when I say quickly. I will not talk about computer complexity of nothing of the sort. I will try to keep the talk in a very informal and light way. Okay, so if we can verify quickly that a candidate solution is indeed a solution for a problem that I try to solve, then we say this problem belongs to NP. Okay, and we know many problems in NP where we can calculate or compute a solution quickly. Not only we can verify a candidate solution quickly, we actually have a way to find this solution quickly. For example, if we want to sort a set of elements, and someone came to us and says, this is a solution for this problem, we only need to check that the solution is sorted and it contains the elements that we want to sort. So we can verify quickly candidate solution, but also we have algorithms that can produce, calculate, compute the sorted elements. They can sort the elements by itself. We can not only verify, we can produce the result by ourselves quickly. And we also know many problems that we don't know. We can verify a solution quickly, but we don't know how to compute, say, solution quickly. The example that basically everybody uses is the traveler salesman problem. So we have a traveler salesman, and he has to go to several cities to sell whatever he's selling. And we want he to start in one city, probably the city where he.
Perdón, Canek, no estamos viendo nada y no vimos los cambios de.
Sorry, I don't know what I did.
Ajá. Dice que necesitas darle.
Sorry, I paused the.
Okay, now it's.
You are seeing my.
Yes, we see now.
Okay, sorry about that. I moved the little thingy with the controls and I paused the sharing by mistake. Okay.
We are see the slide of NP problems.
Perfect. So we also have the travel salesman problem. We want the travel salesman to start in one city, travel all the other cities, and finish where he started, what we call a cycle.
Again is paused.
Sorry?
It's paused. La pantalla está pausada.
Yeah, I'm not moving.
Okay. No, pero
sorry.
no se ve. Yo no la veo. No sé los demás.
It says that my screen is sharing. I don't.
The rest of the people is watching.
Yeah,
the
I
slide?
see it.
Yes,
Well, here it
I
says.
hear
Okay, so then it's my problem. Sorry,
Yes.
thank you.
Sorry.
Here it says that your screen sharing is paused.
It's paused?
Yes, that's what appears from my computer.
Do you see changes in the screen?
No changes at all.
Okay, I will stop the sharing and we'll start again to see if
Sure.
that fixes the problem. So my screen is showing?
Not yet.
Not yet.
Not yet?
No.
This is how many computer scientists do you need? I don't know. It says that my screen is shared, and I cannot see that it is being shared, but I don't know if it's.
No, it still is not sharing. Just
Okay,
showing
let me try one more time, and then I don't know exactly why. Wait. Oops, I think I'm. So I don't know why this is happening. I'm not sure what to do. Maybe I disconnect and try to connect again.
Maybe it
Okay.
will work.
I will do that. Sorry about this. It has never happened to me. So I will leave. I will try to enter again.
Okay, no problem.
Hi again. Let me try again, and then otherwise you will have to believe me when I tell you about the images. You can see my screen? No, you can't, right?
No.
No, only a black screen.
Only a black screen. And now.
Did you send very fast to?
Yes. Please send me an email to send the presentation.
Okay. Julian, can you put in the
chat?
chat, please?
Chat, sure.
Sorry about this.
Don't worry.
It's probably my fault for using Linux.
No. Okay, maybe. But
I see the email. Give me 1 moment. Cartoonam. Okay. One second, please. I just sent it.
Okay, let me download it.
I will prepare a comic video for the next time for this situation because always happen.
Sorry for the problems this work.
No,
Okay, thank you. I was in the MP problems, I think. The next one? Yes, perfect. That's the one. No, before? One before? Thank you. I will sell next, and please put it in next. So in the traveler salesman problem, the thing is, if someone came and gave us a possible solution for the traveler salesman problem, we can quickly verify that it is indeed a cycle of the cities that the traveler salesman wants to travel to, and we can check also quickly that it indeed uses all the cities we want. However, we don't know how to quickly computate this cycle. Next one, please. This do not mean that such a quickly way to find the solution does not exist. We haven't just found it yet. It is possible, although improbable, that there is a quick way to find the solution, but we just don't know. Next, please. So NP-hard, thank you. The NP-hard problems are problems that if somehow we find a way, any of them, to solve them quickly, then we can solve all the problems in NP quickly too. So in this way, they are like even harder, the most hard problems in all of NP, and some of them aren't even in NP. Next, please. Some NP hard problems are also NP problems, so we can verify quickly the solution, like the traveler's salesman problem. Next, please. When a problem is NP and NP hard, we will say that is an NP complete problem. Next, please. Many NP complete problems are decision problems. They have an answer that is yes, no, true, false, exist, do not exist. For example, the traveler salesman problem. The problem is we don't know if such a cycle that travels all the city for the salesman, if such cycle exists. Next, please. And many NP hard problems, not in NP, are optimization problems. So in that case, we are not only interested in the decision problem, not only we want to know if the cycle exists, we actually want to know the best problem, the best solution. So not only one cycle of this series, but the cycle with minimal distance, with minimal cost to travel or minimum time. We want to optimize something. This is usually the case. Next one, please. So this is the sorry state of this question, whether NP is different than P. It has been decades since this question was posited, and basically we don't know. It is possible that they are equal, but most people believe they are different. But at some point, someone solves any of the problems in NP complete in a quickly way, then all the problems in NP basically becomes the same as P. Next one, please. So the problem with NP hard problems is that they are hard. We don't know how to solve them quickly. Next, please. We don't know if it's possible to solve them quickly. The thing is, we have only been able to prove that they are the hardest, but we don't know if we cannot prove up until now if it's not possible to solve them quickly. We just know that we are not able up until now. And besides that, if someone somehow produces a solution and says, oh, this is the best solution for this problem, we have no quickly way to verify if this is true. The only thing usually that we know how to what to do is to check all the possible solutions, which are an astronomical number, to try to verify if it's indeed better than the other ones. Next, please. And we need to solve these problems. Most of the interesting problems in everything, in electoral problems, in population problems, in energy problems, in a lot of stuff, are NP hard. And since we don't know how to quickly find a solution optimal for a optimization problem, next please, we settle for finding a good enough solution relatively quickly. Okay, next please. And there are several ways to approximate these good enough solutions. In this talk, we will talk about heuristics for combinatorial optimization, which is the technique that I actually use in the electoral authority here in Mexico with David Romero, and that I wanted my students to start to learn how to program, how to code these solutions. Next, please. So heuristic, sometimes called meta-heuristic in the literature, there is not a consensus exactly what we're talking about, if it's an heuristic or meta-heuristic. Basically, it does not guarantee to find the optimal solution. Next, please. What it does is explore the solution space, which, as I mentioned before, is astronomical in size, but it basically tries to search it in a smart way, trying to find good enough solutions in it. But it cannot search all the solution space because it's huge, it's cosmically huge. And also, and this is important, we cannot only try to improve our solutions all the time, because if we do that, inevitably we find ourselves in local minimums. So in a solution that is the best in its neighborhood, but probably it's far away from the optimal. Next one, please. To do this search, to do this smart search, sometimes we must allow the heuristic to actually worsen the solution, to choose a worse solution than the one we have at this moment, exactly to allow it to escape local minimums and try to search better solutions in other parts of the solution space. In many cases, the heuristic utilize metaphors of natural processes, like how a bee colony explores for food, or how the annealing process improves the metallurgical property of alloys. Next one, please. We will cover 3 different NP-hard problems that my students try to code, to program system to solve them, and the heuristic that they decided to use to solve these problems. Next, please. So the first one is group assignment with water flow-like algorithm. Next one, please. This one was I showed the name of the title of the thesis in Spanish in these slides, because this is how you can find them in TesiUNAM, which is the electronic database that our university stores all the student theses. I think there's basically all of them since the beginning of the university, but this one was implemented, and the thesis written by Alejandra Cristel Coloapa Diaz, and actually it was a finalist in the thesis award for bachelor degree in the Congress of the Mexican Society of Operational Research. Unfortunately, the jury decided not to give her the first prize, the bastards. But I'm really proud of the work that Alejandra did. Is really nice. Next one, please. So what Alejandra did was try to solve the problem of group assignment for the Escuela Nacional Preparatoria number 6. We have a high school system integrated with the national university here in Mexico. It's a whole thing. And basically, the problem is how to assign students into group in a high school. Next, please. The students make a choice of what groups they would like to be in, and this preference must be respected when possible. Next one, please. And several restrictions on the assignment of groups must be satisfied. The groups must be balanced. So we don't want, well, the preparatoria says don't want groups with only people with good grades and then some groups with only people with bad grades. This is pedagogically considered a bad practice. It has to be balanced. There have to be students from all kind of average to be in the same group. There must be no empty groups, also no groups with too many students, etc. Next one, please. And this is a particular case of a very famous NP-hard problem, which is the general assignment problem, which is the problem that we have some tasks that must be performed, and we have some agents that can perform the task. How we assign the agents to the tasks? If it's a really hard problem to solve. Next one, please. So to solve them, what Alejandra did was implement a variation of the water flow-like algorithm. This heuristic was proposed by Fengcheng Zhang and Yuanpeng Wang in 2007, sorry, for object grouping problems. Next one, please. They use it exactly to solve the Traveler-Selman problem and assembly lane balancing problem. Next one, please. What the heuristic tries to do is the solution space for the problem, it visualizes if it was a terrain. I mean, we can visualize this in 3D. Obviously, the problem has many much more dimensions. So, but imagine that is in 3D. So we have some hills and some valleys. What we what the heuristic tries to do is emulate how a flow of water will traverse this problem space. Naturally, by gravity, the water flow will flow to lower grounds instead of high grounds. However, also by gravity, if it's too strong, the flow to the bottom, it can reach enough potency to actually start to go up. And this is what allows this heuristic, what I was talking about moments ago. It allows to escape local minimums and try to search solutions in other places. This is important. All of these heuristic, we don't want them to get stuck in local minimals. We want them to explore the space solution and try to find better solutions all the time. Next one, please. That's what I was saying. A strong enough water flow can go down, and then it has enough strength to actually start it to go up. Next one, please. So Alejandra was a student in this high school, the NP, La Escuela Nacional Preparatoria, number 6, and she was friends with some of the administrators there, and she actually got the data without names, of course, respecting privacy laws and etc. But she got the data and actually did the job that they were already doing to assign groups with 1,029 students in 18 groups with a maximum capacity of 58 students per group, with 5 preferences per student. Next one, please. So this is the result that the high school, the administrators in the high school, were able to come to. They use a greedy algorithm to try to do the assignment, and then they made manual adjustments. So this is the actual solution that the high school was able to obtain. Next one, please. And this is the solution that the system that Alejandra coded was able to produce. As you can see, it's so much better balanced. So you can see the average grades of the students are much better balanced than in the solution that the high school produced. I actually don't know if Alejandra offered the system to the school. I haven't talked to her since she graduated, but apparently her system was able to produce much better results than the greedy algorithm they were using, which is not surprising because these problems are really, really hard, and this is exactly the advantage that using heuristic to solve them provide. Okay, but I'm going to talk about the work of my students in this way, not going deep in the part that I was interested when I was working as their advisor. So these systems my students program were not little programs that solve the problem in hand. No, they were actually software engineering sound systems with good programming practices and unit testing and all the things that we teach the students of computer science in the Faculty of Science in UNAM. Which is the reason our graduates find jobs basically without any problem. I'm just talking about the heuristics and the problems, but part of the value that these students produce is exactly the software the software development process that they follow to write these programs. You can check the thesis. They are in Spanish, of course, but they document all the software engineering practices that they make, the design, the analysis of the problem, and all the things that one as a professional programmer must do to produce a sound system. Next one, please. So the next one is my student Carla Socorro Garcia Alcántara, which wrote her thesis in ant colony optimization to the firefighting problem. Next one, please. The firefighter problem is really interesting. So we have a graph, and we start with some vertices that we want to protect and some vertices already on fire. Okay, and in an iterative process, the vertices on fire it spreads the fire to its neighbors. Okay, and the idea is to put firefighters in vertices to stop the fire from spreading, with an emphasis on protecting some very specific vertices, which in a real situation will be, I don't know, an orphanage or a school or a hospital, something that we cannot allow to be consumed by fire. Next one, please. The same model for fire propagation in a fire can be applied to a flood of water in a city, for example, or how a virus spread in a population. It can be a computer virus in a network, or a human virus in a pandemic, which already we know we all have experience of how that turned out 5 years ago. Next one, please. We have several choices to what we want to optimize. We can try to maximize the number of vertices saved, vertices not burned, or we can optimize the number of firefighters used. It can be tailored to different settings, the problem, because the firefighters are limited resource, so we cannot assume that we have as many as we want, or we cannot suppose that we can send all our firefighters to one single fire. Or we can try to say, no, doesn't matter how many firefighters we use, try to save as many vertices as you can. Next one, please. And the problem changes enormously depending on the topology of the graph. For example, if the graph is a tree, it works in some way. If the graph has only vertices with 4 degrees, for example, it can be actually solved in polynomial time. Next one, please. So the heuristic that Carla uses to solve this problem is the ant colony optimization, which is a very known heuristic to solve this kind of problems. It was proposed by Barco Dorigo in 1992. Next one, please. And the heuristic tries to emulate how an ant colony searches for food, finding optimal paths to reach this food. What the ants do is, when they are walking, they leave a trail of pheromones in the ground. So if the ant finds food, it travels back to the colony using the same path, and then more ants will try to follow this path, leaving more pheromones and increasing the number of pheromones in the path. Paths that are not successful, that are not the best route or to the food source, or actually don't go to a food source, many greatly reduced number of ants will use that path, and then the pheromones will not be traced in the path. And in the execution of the heuristic, the pheromones are evaporating. So at some point, bad paths that are too long or that don't go to good food sources will be abandoned eventually. Next one, please. What I was saying, the most traveled paths will have the most pheromones, and the less traveled paths will lose pheromones through evaporation. Next one, please. So when an ant in the heuristic, when an ant needs to choose what path to follow, not necessarily will go to the best path, which is what I was talking about before. We don't want to choose the best we know all the time, because if we do this, inevitably we get stuck in local minimum. So we give the ants the chance to go to a different path, probably with less probability of choosing a worse path, but it has the opportunity to do that. And then perhaps it will lead to a better path eventually. Okay? So next one. So Carla used a synthetic data set, a randomized data set that she generated in a grid of 23 by 23 vertices, 529 vertices in total, with 50 diagonals to make the problem interesting. Next one, please. So this will be our initial grid. You can see in green the vertices we want to protect, and in a diagonal in the middle of the grid, you can see in red the vertices already on fire. Next one, please. This is the solution when we want to optimize the number of firefighters. This solution rescues all the green vertices. They do not get on fire, and it uses only 89 firefighters. Of course, a lot of other vertices get burned, but the vertices we were interested in saving, they get spared by the fire. Next one, please. This one optimizes the number of vertices solved, not only the ones we are interested in saving, but also maximize the number of vertices saved. In this case, we need to use 159 firefighters. And if you see these two solutions, you may think, whoa, a lot of vertices got burned. And yes, that's exactly what happened. If you remember this year in California, at the end of last year and the end of 2024, there were several fires in California, and they destroyed a lot of houses. The same thing it happened in the pandemic in 2020. When this kind of stuff start to spread, the thing is we need to allocate our resources to try to save whatever is most important. We will not be able to save everything, because the fire or the viruses or the flood spreads really, really quickly. This work that Carla did was really nice. She did an research stay in Barcelona, working with people that were specialized in these kind of problems. And it's also, I'm really, really proud of the system that Carla coded. Next one, please. This is the last one. This is the Steiner tree problem with particle swarm optimization. Next one, please. This was at the thesis written by Marisola Mezcua Lopez. She's of this group of 3 students, she's the last one to graduate. Next one, please. And the Steiner tree problem, we have points in the plane, and we want to add more points in such a way that the minimal spanning tree, the tree with edges, edges formed by segments between the points have the minimal longitude in all these edges. We want to add points such that this minimum spanning tree is optimal, is the smallest possible. Next one. This is used to design a very large scale integration in circuit integration. The trace, we have different components in circuits. The traces, which is paths of copper that connects the electrical signals between the components, we want them to be the shortest way possible. So this is a problem used to solve this kind of problems. Next one, please. It's also used in multicasting for network optimization. Next one, please. Also is used to determining phylogeny, which is an evolutionary tree for a given set of species using protein sequences. Basically, we have some species and we have the evolutionary tree between them, and we know that we don't have the archaeological record complete. So we try to guess where a missing link is in this evolutionary tree, and with the Steiner tree problem, we can try to optimize where these species in the genetic code will be. Next one, please. To solve this problem, Marisol used particle swarm optimization, which is another heuristic really well studied. And it was proposed by James Canek and Russell Everhart in 1995. Next one, please. And this heuristic tries to emulate a simplified social model, artificial life, or perhaps a better way to see it is the behavior of bird flocks. We all have seen in the sky when a flock of birds fly. With at first sight, it could seem that it's random, but actually they follow each other in some way. Next one, please. So each particle in the heuristic changes its position at velocity in relation with its current states, try to find good solution, and also the states of the neighbors. In this case, in this heuristic, the strategy used to escape local minimums is exactly use all the swarm. The swarms search not only point by point, but like in group as a swarm. Next one, please. The swarm explores the solution space, what I was saying, allows to escape local minimal because each particle is not looking only its solution and perhaps close to it, but also its neighbors, the particles more close to them. Next one, please. I will show, next one, please, a synthetic random data set that Marisol used. This was the original set of points, next one. And this is the solution that she found. The aqua vertices are the Steiner points that she added, and she actually improved enough the set of points. Marisol took an article, and it had the points in the article printed. The authors didn't publish the coordinates of the set of points. So Marisol basically used the image in the computer and calculate the coordinates on the points, and then she executed her system in this set of points and actually improved the results of the paper. And she was really excited about this, and I had to tell her, I mean, it's really good. Probably you were able to reach the same results as them, but the improvement that you are seeing is with almost 100% certainty, because we don't have the exact coordinates of the points. try to extrapolate it from an image. Anyway, the system that Marisol programmed also works really well for this kind of problem. I'm also really proud of her work. Just to finish, all three students which work I presented in this talk, they are professional programmers. That's what they do. Unfortunately, I haven't been able to convince them to study to go to postgraduate school, but I keep trying. And well, sorry for the technical problems. Next one, which with this I will. Next one. With this I will finish. Thank you.
Thank you very much, Canek. I don't know if we have some questions or comment. Nobody? Okay, so I like to say some things. First of all, to thank you very much, Canek, for your talk. For me, it's always difficult to understand this MP complete, etc., because I don't know about this topic. So I used to say my student that it means that it's not possible. And and then with this type of talks, I start to understand better this not possible. So thank you very much. The second is that it's very interesting, this work of your students, because in the first example, I immediately think in our faculty, because sometimes we are not conscious to the problems, to some problems, but maybe some of you don't know that our faculty has actually more of 10,000 students, and we have more of 1,000 group. This is a real information. So this is one of the reasons, and we have 100 classroom, more or less, or a little more. So this is the reason that we have to start class at 7 a.m. and finish at 10 p.m., continue during all the day. The distribution, the organization of these groups is really very big problem, because we see your example for this group of the Escuela Nacional Preparatoria. So to do the same for our faculty, I don't know if it will be interesting or not. And
I had offered my students for them to do, but they don't pay attention.
Yeah, maybe you have to look for new students for this problem.
No, the students are willing to do it. The authorities in the faculty are not interested in
Oh, really? Okay. It happens, yes. And about the second problem, I would like to talk with you later, because I think it's relative to some things that I do it. So it can be interesting to talk about this. And in general, I like to say thank you, because I think it's very nice that the people that see this talk has opportunity to know how work our students, what means to have a bachelor thesis in our faculty. Is really very strong. Is in general, they are very interesting problems and require a lot of time, a lot of work to our students and the advisors. So thank you very much for this very nice talk again.
Thank you, Rita.
Yeah. So if there is no more comment, or I don't know if somebody like to say something or not. No? Okay, so I would like to say thanks again to all the invited speakers, all the participants with video talks and posters that you can see in our YouTube channel for permanent. And to say that I hope to see you again next year. And now I would like, if it's possible, that you stop your camera, you put your camera, and we will take the last picture of this year. So thank you very much to everybody, and see you next year. Bye-bye. Thank you. Ready, Julie?
Okay, so smile for the photo.
Okay, we smile for the pot.
There it is.
Okay. Thank you.
Well, with that photo, we finished this year's card, and I hope everyone likes it. And don't forget to follow us on YouTube, on Facebook, so you know for the next year when will the card start. And don't forget to see the contributed talks and posters of today. They're quite nice. They are already on Facebook and on YouTube.
Okay, thank you, Julie.